Okay, today we're working out of 4.2, and in 4.2 we're going to start studying logarithms and what we mean by a logarithmic function. Logarithms are used all over the world to study things like earthquakes, decibels in hearing, brightness of stars, a lot of things that honestly their magnitude is quite large, and so we want to quantify it maybe a different way, shrink that number down a little bit, and logarithms can help us understand that. When we're talking about exponential growth, logarithms can help shrink those values down a little bit, or help us understand those values a little bit better. So the definition for a logarithm, this is important. X has to be greater than 0 and b has to be greater than 0. So this base and what we're taking the log of both have to be positive. The only thing that's allowed to be negative is the object over here. Okay, so a couple of different ways to look at this. When we talk about logarithmic form, we're saying that y equals log base b of x. And that is interchangeable with its exponential form. Now, the nice thing about the exponential form is certain stuff is consistent. For instance, b is the base over here in the log, so b will be the base of the exponent. And every logarithm equals the exponent. So this logarithm equals y, meaning that y must be the exponent. And it's left to equal whatever was in the parentheses, x. Another way to think about this looks like b has the exponent of x. It doesn't really have that, but it might look like that. And so we can't keep b with the x, because that would just be redundant. So b must go with the y, and so we end up with the second form. These are interchangeable, and we're going to use both in order to solve questions, okay? So if we look at some of these, we're going to rewrite them in different forms. We realize the base is the base, so the base of the log is 5. The logarithm equals the exponent, so 2 must be its exponent, so 5 to the second equals x. Well, what is 5 to the second? Well, it's 25, so x would be 25. Now that's solvable. Over here in the log form, it's not solvable per se, but in exponential form it is. We'll continue that process here. This should be 7 to the third. Remember, the log equals the exponent, so the exponent must be 3 equals x. Again, we can solve that. This one's an interesting question, okay? Because right here, b is our base. We don't really know what b is. But b to the exponent of 2 equals 25. Well, this is actually pretty solvable. We don't technically know what b is, but we could take the square root and we would get, that b is 5. Now, interestingly enough, if I took the square root, I'd have to do plus or minus root 25, which makes it plus or minus 5. But we said earlier that this number here and this number here cannot be negative. And so I can't use the negative 5 as a b. But these are solvable in one form, not solvable in the other. And that's sort of the key that we want to point out. We come down to these exponential forms, and we say, well, let's rewrite them in log form. Well, this is maybe a little bit trickier at first, but you'll get the hang of it. The base of the exponent, which in this case is 3, is the base of the log. So I'm going to do a base 3. And I always like to jump to the end. I know the log is supposed to equal the exponent. And since the exponent here was 2, the log here needs to equal 2. Well, the only thing left is the x, so we're going to slip that in there. Okay. So this one would be log base 6. It must equal 3 because the exponent was 3, leaving me with x to put in here. And then this last one, log base y, must equal 4. And what's the something? It'd be 81. So we can see this interchangeable nature between exponential and logarithmic form. It's like translating from English to Spanish. We have to be able to go back and forth and use both. There are some consistent logs that we want to know when we reference the number 1. For instance, log of b is 1. And that's because b to the first power will equal b. So anytime you have the same base and value right here, log of 3, base 3 of 3 would be 1. Anytime we have that set up, we're going to get 1. And consequently, anytime we have a 1 in this position right here, in what we call the y position, so let's say I have log 7, 1. Anytime there's a 1 there, it automatically equals 0 because 7 to the 0 power is 1. Now there are a couple of inverse properties. If you have log, let's say, base 2 of 2 to the 7th, okay, the log base 2 and this 2, these three pieces right here are going to cancel each other out, and you're left with 7. Whatever the exponent is on top of everything is going to end up being your answer. Consequently, if you have 7 raised to the log base 7 of, say, 10, this stuff right here is again going to cancel itself and give us 10. So when we have the base of an exponent and the base of the log matching, whether it's inside the log or outside the log, base of the log and the base of the exponent match, they tend to cancel each other out. And we get the exponent or the other piece left. Well, a logarithm and an exponential are inverse functions, which means that quite literally, if we were to draw a line right through the center of the coordinate system, we would see a reflection. In other words, this point would fold right on top of this point. This point would fold right on top of this point, and so on down the line. We can find matching points that if we folded the page in half, we would have them line on top of each other. So 2 to the x, y equals 2 to the x, is an inverse to y equals log base 2 of x. These are inverses, and they're also reverse versions of each other. One's log form and one's exponential form, but both have that same structure. The domain for a log is a set of all positive numbers, okay, traditionally, because remember, we have to have a positive there. Okay. However, if we shift it, we're going to shift that as well. If you remember the exponential graph looked like this, and there was always that range restriction. There's that place where it can't go down to. Remember, this has been reflected. And so now, instead of having a horizontal asymptote, it has a vertical asymptote. So this is a log, and this is an exponential. And so if we move this way or this way, the domain will be shifted to be greater than 3 or less than or greater than 8, but typically it's greater than 0 because we can't have 0 in there. So let's take a look example at this question. This says x plus 3 in here. Now remember, we're allowed 0, but this cannot be a negative number, okay? Because we can't have negatives in here. If I put negative 3 in here, that's okay. Yeah, I can get close to that, but, well, actually it has to be greater than 0, so it can't be 0 or negative. It's got to be greater than 0. So if I put negative 3 in here, that would become this boundary line, okay? Because negative 3 would make the inside of that 0. And so we would say the domain is from negative 3 to infinity because it's greater than negative 3. Common logs. A common log is base 10. So when we write it without a base, okay, like this, we mean base 10, even if it's not written. Okay. So some of the common things we need to know. Log of 1 is 0. Log of 10 is 1. Right, because we're thinking about, remember we said that anytime you have a 1 there, okay, that's going to be 10 to the 0 equals 1. That's essentially y. Here, remember this is 10 to the first equals 10. So that's why we have a 10 equals 1. Because remember, these logarithms are finding the exponent. That's what we're looking for here, guys. These logs should be finding our exponent. Well, 10 to the x would equal 10 to the x. And there's my exponent. It was x. And here, you remember this is 10 here. So we have this, remember we said that the 10 and the log base 10, we're going to cancel each other out and leave us with x equals x. So those are some of the common rules Now, we do also use natural base or base e. Okay, and when we use base e, this number here, we use ln. You'll see ln on your calculator. I prefer to just do a script ln, but that's your choice. Try not to make it look like a 1 like that, okay? Because if you do and you do this, some people will think it's 21, and that's no good. So here I have ln of 1. Remember, this is base e, because e to the 0 is 1. Anything to the 0 is 1. Now this would be e to the 1 is e. There's my exponent, same kind of deal. I'm finding these exponents. Here it's e to the x, that's this guy, equals e to the x. And then again, e and ln base e, because it's base e, they're going to cancel each other out and get x equals x. So these properties, we're going to use them a lot in solving and isolating. We can use our calculator to do some of it, but there is going to be some need to know some of the basic rules. Good luck, and we'll see you in class.